Hello, hello, hello. We have less than 6 weeks left in the school year. Did you know that? That's pretty cool. And for us, we're going to finish content today. Now, it doesn't mean you stop coming to class, and it doesn't mean that we're not going to keep learning as we advance. But as far as AP exam new content goes, we're going to finish the curriculum today. So congrats to you for making it here. And we're going to keep our dive in electrochem. Hey, for those of y'all that have been checking out the roadmap, though, you'll notice that it says you have a quiz on Thursday for me. That is not something that you need to be stressed about or cramming for, because that quiz is going to be open note. There's not going to be a timer on it. It's going to be resumable, and you're going to have several days. So it is important, and I'm going to give you full details when I see you on Thursday. But I don't want you to see that on the calendar and be like, well, man, I better make sure I know my electrochem in the next 48 hours. I mean, I hope you know your electrochem, but it's not going to feel like a test. So relax, just keep practicing your stuff and focusing. But I don't want you to be stressed about Thursday. But again, on Thursday, I'm going to give you full details on exactly what our AP exam prep will look like, what that quiz looks like, and all the cool stuff that I have waiting for you as we revisit everything from the school year to get ready for the exam. So that's coming Thursday, but we need to finish electrochem. So if you would, you do need a calculator, your Faraday electrolysis slides, and your reduction potential chart, please. When we started this unit and I introduced cell potential to you on lecture 1, I told you that the other 2 lectures were going to be pretty much devoted to what it looks like when a cell is thermodynamically favored. That was voltaic cells. And when it's not thermodynamically favored, meaning it's got a negative cell potential, E. And that is today electrolysis. However, before we get into that bulk of our focus, there's a couple final equations on your AP sheet that we've not yet covered, and they fit right here. And so we're going to open up with 2 new equations. They're plug and chug, so I don't think it'll be a big deal, but you'll see how it definitely fits nicely into the end of electrochem. So what you're going to see right away is the re-emergence of delta G. What you might remember is we calculated Gibbs free energy back at the beginning of this semester when we studied thermochem. Does anybody remember the fun name of the equation that we used to calculate delta G back then? It had a fun name. It was called Ghetto Homies. That's right. That was Ghetto Homies. And Ghetto Homies is a totally cool way to calculate the free energy of a system. However, if the data you're given is not entropy and enthalpy stuff, those were the delta S and the delta H's that we were studying back then. If instead you're provided with cell potential data, well, then you would need to use Faraday. All right. And so you'll notice that my calculation of free energy here is going to use cell potential. All right, there's the E. But you see the F there? That's a new variable for you. So F is Faraday's constant. You don't have to memorize this equation. You don't have to memorize the constant value. It's that big number there. They're on your sheet. Faraday is going to be the amount of charge that 1 mole of electrons carry. All right, and when we put that energy in, along with cell potential, we can find out the free energy. So we're going to be using that big number. So let me show you how it all marries our concepts together in a problem. Now, what's cool about this problem is it's going to actually introduce both of the equations, because while it's asking for the free energy, It also asks for the equilibrium constant, and you probably remember that the equilibrium constant is variable K, and you'll see a secondary equation down here that uses K along with free energy, another given equation. This is a really good problem because it's very FRQ-y, and what I mean is that the way the single question's written, it splices through 3 units. All right, it brings a thermo concept with an equilibrium concept with an electrochem concept all into a simple 1-sentence question. So you've got to know quite a bit to get your head wrapped around what it's asking here. You'll see that the slide helps you identify where we're going to get variables from, so I tried to be helpful. But notice how this is a real good cross-cutting of topics. So in order to find the free energy with our new equation of delta G there, we need the cell potential, all right? We are given a redox reaction, and we know that it's time to take attendance. Huh. That is news to me. Give me 1 second. Apologies. I was saying something. Okay, to get started, you can see that we've got this redox reaction. All right. So in order to find the cell potential, let's analyze the half reaction so that we can get a value for E. So be looking at this reaction. Same thing. We're going to be connecting, or rather writing half reactions of the parts that are obviously connected. All right. So it looks like initially, so small. Magnesium is yielding magnesium 2. So here's one of them. Magnesium is going to be yielding magnesium 2. The other half reaction I can pull out is going to be lead 2 yielding lead. All right, we're going to have lead 2 yielding lead. I'm going to follow my half reaction rules, which is easy here because there's no balancing of hydrogens and oxygens like on the harder ones. Instead, I only need to fix the charge. So it looks like we're going to have 2 electrons there and 2 electrons there. And that's going to go ahead and balance everything. All right, so now we can find the reduction potentials on your handy dandy table. All right, I can tell that the top reaction is automatically oxidation because electrons are a product. Therefore, when you find it on your chart, you need to flip the sign because it's oxidation. And when you do that, you're going to get a value of positive 2.37. My bottom half reaction is definitely reduction because electrons are a reactant, so we can use the value on the table as is. And when I do that, I find negative 0.13. All right. right, so the sum of these two values will give me my overall cell potential of 2.24. So there's an intermediate answer that will help me out. But remember, I'm trying to find the free energy here, so let's plug into the rest of this equation, and you'll see that delta G, all right, is going to be equal. Now, notice there's a negative sign there, so follow your equation carefully. We've got N stands for the common number of moles of electrons in the half reactions. Now, they're already the same. Remember, if they weren't the same, we would multiply one or sometimes both of the reactions to make them the same. But they have to have the same number of electrons. So you'll always be able to find a single number there. In this case, it's 2, is the number of electrons that the half reactions have in common. F is Faraday's constant. It's the big number. And my cell potential is 2.24. Give you a moment to try to beat me. I get 432,000 negative. Okay. It's going to be joules energy that we're measuring. All right, and this is one of my answers. But there is a second question. Let's talk about that number for a moment, though. First off, it's given in joules, but you might remember from thermo that delta G is commonly discussed in kilojoules. So don't be surprised when Schoology does that, all right, because this is only 432 kilojoules, which is a much nicer number to discuss. So watch that unit jump. However, joules is useful here because the secondary equation we're about to use that uses R requires joules. So you've got to be very careful with your units as always. Hey, look at my cell potential value. Is this spontaneous or non-spontaneous? Spontaneous because it's positive, right? Hey, look at delta G. Do you remember what it meant when delta G was a negative value? Thermodynamically favored, spontaneous. My point being is that these two values are agreeing with each other, which of course they are, all right? But just review that a negative free energy is spontaneous, just like a positive cell potential is spontaneous. So hooray for conclusions. Now, let's move to the second part of the question that goes and connects it to equilibrium, which will give you an equation that connects free energy to K. All right, so another one that is your buddy. Now, I want to point out that the R value is about to show back up, but it is not the same R value from gas laws. Gas laws was funky in a few different ways, right? It uses the R of 0.0821. Everywhere else is going to use the R of 8.31. All right, it's on your sheet. It's actually right below the equation on your sheet. So they don't try to be tricky with the constants. But the other thing that was different in gas laws was that standard temperature was 0 degrees Celsius, right? Well, now that we're out of gas laws, we're back to the normal standard temperature that everything else uses, which is 25 degrees Celsius. So make sure that this differentiation's in your mind. I went over that in lecture 1 with you, all right? But have that R value handy as we plug and chug here. So we're solving for K. My free energy is a big number. All right, notice that we've got negative R. All right, so we're going to go negative 8.31. It needs a temperature, and you'll notice that everything has been at the naught, which means standard. Therefore, the temperature is 25 degrees Celsius to 98 Kelvin by adding 273. And we're going to solve for the equilibrium constant. Notice that natural log has popped back up, but we know how to handle that. All right, so we can simplify here. Hey, you notice how both sides have that negative symbol? So that's kind of like it's not there at all. So those are going to go away. But to start simplifying, I'm going to divide my large number here by the product of these two numbers here. And I get an intermediate answer of 174 for the natural log of K. We don't want the natural log, though. We want just the equilibrium constant. Do you remember how to inverse natural log? It's just the secondary function of that button on your calculator that gives you the E caret symbol to 174. Notice how the K value is quite large. But I mean, how large it is can be good for comparative reasons, but usually for conclusion reasons for the equilibrium constant, I care about whether it's less than 1 or greater than 1. I know that when K is greater than 1, the products are favored, which means the reaction will just happen forward spontaneously, which agrees with every other value that we've gotten so far in this problem, right? So it's a big agreement across all these different divisions of units that we've been covering. I don't think it's necessary for us to keep plugging and chugging after all this time we've spent together. So Schoology will give you more practice here. So let me know if Faraday messes with you at all. But our main focus today is going to be our non-thermodynamically favored cells. They're called electrolytic cells, all right? E is going to be negative, which is the most obvious mathematical difference when dealing with these. But there are some other general differences. I mean, there's actually only a couple of them, but they're pretty big in regards to the way it looks if you are asked to draw a sketch, and a couple of the things you're going to have to think about during electrolysis. Now, I want to let you know that historically on the AP exam, it's not always true. They've asked you to draw both galvanic, the voltaic, and the electrolytic cells. But they ask you to draw voltaic far more often, which is why I focused big time on you being able to draw those. We're going to draw electrolytic, but these questions tend to end up in the multiple choice more often than they do the FRQs, just pinpointing different things that are happening. I'll give you a couple examples as we go through our explanations today, but I'm just speaking historically. It could be absolutely wrong for what they're going to do to you next month, but I would expect most of what I'm about to cover to be in the multiple choice section. So here's one of the most noticeable differences in a sketch, or really just in reality of what's happening in an electrolytic cell, is that there will only be one container instead of two. Inside your battery, there's a separation of two containers that are connected by a wire passing electrons. In electrolytic, everything's in a singular container, which changes a lot of the mechanics of what we're going to watch happen as the process goes. That one container that we're going to deal with is still going to have two electrodes in it. One will be a cathode and one will be an anode. However, the electrodes themselves will not play a role in the reaction this time. If you think back to the voltaic cells that we drew and analyzed, the electrodes were a big part of causing the oxidation and reduction to be driven. In electrolytic cells, the electrodes are going to just be catalysts that allow a surface for other reactions to take place. Because of this, it's important if you're setting up an electrolytic experiment that the electrodes are inert metals. Remember back in voltaic cells when we would build the salt bridge to get rid of any charge buildup? We had to make sure that the item inside the salt bridge would not create a secondary reaction that would throw off everything. Same thing here. You don't want to go and choose an active metal for your electrodes that are going to interfere with what you're trying to accomplish through the electrolysis. You want to instead use an inert metal, something like platinum. I always choose platinum when I'm setting up an experiment on a drawing. Other inert metals that I've seen AP use are things like tungsten and titanium. I don't think you would need to know that list, but if you'd like to jot them down, I think that the three best electrodes to use for electrolysis are tungsten, titanium, and platinum. Because they ain't gonna react with what you're trying to accomplish. All right. I am not going to show and read these next three slides to you, all right? Everything I'm about to do in my initial electrolytic drawing is going to cover everything that's in here. And then when you go back and read and it says little tidbits of info, you'd be like, oh yeah, it was in my drawing. All right, but I'm not gonna read through it. What we are gonna do is just go through a from scratch example of electrolysis, and then we'll do some extra practice behind the scenes. But I'm covering all three of those slides simultaneously. There are many different electrolytic situations, all right? Again, making a system with a negative E that doesn't want to be spontaneous, forcing it to run by adding energy to it. There's lots of different things you can electrolyze. I mean, you can electrolyze anything, but lots of solutions they could ask you questions about. In my opinion, the most important item for you to understand the science or the chemistry of electrolysis is water. So we're going to do some stuff that's a bit harder than water afterwards, but understanding the electrolysis of water, I believe, is a foundation for answering most of the questions that they'll throw at you. So let's check it out. Are you ready? Let's electrocute water. We've got only one vat in electrolysis, not two. And like I said, our first example is going to be full of water only. We will still have two electrodes. And I like to make mine made of platinum. This is not thermodynamically favored, therefore an energy source must be added. So let's add a cute little battery. It's on all three of the next slides all at the same time. 3 simultaneous slides being covered. Yeah, all 3 before the one that says practice on it. Now, remember that battery that we're using there is a voltaic cell, right? We could like super magnify inside the battery and it would be the other pictures we drew. So that's cool. But what we need to do is connect the electrodes to the battery. I was asked very seriously yesterday if you would lose points if your wires didn't do a loop. Well, duh. No, you wouldn't. You wouldn't lose any points, all right? I mean, really, the number of loops your wire does depends on how much you love piggy tails, in my opinion. But no, it doesn't have to loop at all. I just think it's pretty. And I don't draw many things that I think are pretty. So anyway, so I hope you like my wire loops. All right, so we are connected to the battery. Now, it turns out that the electrodes, as they connect, are going to have charges that match the ports that you've connected them to. Meaning, you could have turned the battery around, right? And had the plus there and the minus there, and it would have made this minus a plus. It's all fine, all right? It's just under here, I'm gonna do the same thing I did with the voltaic and track what's happening on each electrode. So just they're going to match each other depending on where you connected them to the battery. And here's where we have our absolute biggest difference between voltaic and electrolytic. Remember, this is a non-spontaneous cell. And the foundational reason that it's broken without the battery is basically a way to look at it. It's got bad potential, is because there's a reversal of the way that it's set up. In the electrolytic cell, the positive electrode is the anode. And the negative electrode is the cathode. This is an absolute reversal of what I've previously taught you. The way I remember it is based on childhood trauma, because when I was 6 years old, the EPA came and threw me into a white van and kidnapped me for about 5 years. I got to meet new parents. It was weird. We watched Wizard of Oz every day. I don't know. The EPA, they're weird people. The EPA ban is the way that I remember which is which, while I have a ton of chemistry in my head. So you remember the EPA ban also. Here's what it stands for. Electrolytic positive anode, voltaic anode negative. Electrolytic positive anode, voltaic anode negative. Electrolytic positive anode, voltaic anode negative. Just the mnemonic to maybe keep it straight in your brain. Voltaic, the anode is negative. That's our battery. All right, so hooray for trauma. Sorry, that's not a part of the answer. I meant to say that. Sometimes y'all are very literal copying me. And now I erased it and it ruined your notes. Anyway, now, some good news though, all right? Even though the charges are swapped, the processes are not, all right? Meaning that the anode is still the site of oxidation. Remember the vowels line up? And the cathode is still the site of reduction. Electrons will still flow alphabetically, so we're going to have a flow of electrons from anode to cathode. So some things are different, some things are the same. Of course, that's where your studying will come into play. Now, while the picture is, gorgeous, usually for electrolysis, the questions are less focused on an image and more focused on what you're producing at each electrode, all right? We use this process for creating things like jewelry and stuff that is very real world to you by sometimes creating substances that we can't create anywhere else. I'll show you an example. I'll explain an example of that soon. But really, while all of this is true, and you could be asked about any of it, I want to know inside the container what is being created at each electrode. Well, in this example, there's only water. That's all that we've put into the vat, correct? Therefore, the redox that must be happening will be water only. So water's being oxidized and reduced. So for me to figure out what's happening where, if I can write the oxidation reduction for water there and the reduction reaction for water there, I can just see what the products are of each one. Well, you already know which is which based on redox knowledge, all right? Because I know that water, when bonded, has a +1 hydrogen and a -2 oxygen, because those are the oxidation states that you know are true of water. And when it splits, because that's what we're doing, all right, electrolysis is just a fancy way of using energy to split the compounds into pieces. Well, once you do that and they become free elements, they now have no oxidation state because all free elements have an oxidation state of 0. And tracking which is which should be very easy. So here's the answer. Oh, no. That was spousal abuse. Okay, so if water is going to be oxidized, I know the product must inherently be oxygen. How do I know that? Again, because a bonded oxygen is -2, a free oxygen is 0. -2 to 0 is becoming more positive, which is the definition of oxidation. All right, well, for water to be reduced, I know that the product must inherently be hydrogen. How do I know that? Because the bonded hydrogen is +1, the free element hydrogen is 0. That is a loss, that is a dropping charge, the definition of reduction. So this is going to be my skeleton reactions. Of course, then you have to do all of your half reaction stuff. Now, I don't want to burn time doing that from scratch with you because we've had an entire lesson on it. But when it's all said and done, that's what your oxidation will look like. And that's what your reduction side will look like. All the same steps, right? The H's and the O's were corrected, the electrons were corrected. To get an overall equation, I would need to multiply the cathode by 2 because the electrons would have to be the same amount. However, we're not necessarily required to do that unless that's what the question's asking for. And nothing that I'm trying to figure out here would require it because, again, my current focus, I just want to know what is being made inside, or rather at each electrode. All right, so what's being made? The answer is in front of us now. At the anode, we are making oxygen gas. This is going to be bubbling. And those bubbles are going to be O2. Also at the anode, because those electrons will cancel out with the other one, they always do, right? Also at the anode are going to be hydrogen ions in solution hovering around the electrode. What's being produced at the cathode? All right, right in front of us, check it out. That is hydrogen, that is gaseous. We're going to be bubbling over here also. Those bubbles are hydrogen gas. Also at the cathode, there they are. We got these hydroxides. They're ions, so they must be in solution, hovering around the cathode. Here's an example of a question from about 10 years ago. It was a multiple choice question. There was no image, nothing. It was just words, and it asked this. During the electrolysis of water, which of the following best describes the pH environment of the cathode. Listen to my question again. It said, that's all it said. During the electrolysis of water, which of the following pH environments best describes the cathode? And the options were acidic, basic, neutral, or impossible to answer. Look at the cathode. Is the answer acidic, basic, neutral, or impossible to answer? Basic, right? With the picture, most of y'all can see that the cathode is living in a basic environment because of these hydroxides. So it's nice when all of this is in front of you, right? But when you're answering 60 multiple choice questions and you run into that, all right, it's really helpful if you can draw it all out, but I promise it's even more helpful if you just know some stuff about water. All right, but yeah, that's a very complex question written in a very direct and makes it sound kind of like a simple way. And of course, I mean, the most commonly picked answer there, wrong answer, is going to be neutral, because a lot of you chem kids, when you see water in a question and you're asked about its pH, okay, of course if you're guessing, you're going to guess neutral. So it can be inherently very tricky. And I mean, you could even run into the question and think to yourself, oh, well, Cummings didn't ask it like that. All right, there is no chance that I can predict the crazy ways that they're going to cover something I covered in evil little words. All right, so just tread lightly, think through it. But that's a good example of how these questions tend to lend themselves more towards multiple choice than they do pictures for some reason. Any questions before we move on to the slightly tweaked version to end the day? So yeah, so this would be the acidic side, right? Well, I guess you have it in front of you. I would say that this is just for water, in the electrolysis of water, that the anode is building an acidic environment, while the cathode is building a basic environment. I should have wrote it. What if it's not just water that you are electrolyzing and you're asked to figure out what is being created at the different electrodes? So I've got 3 examples here that we will work out together. Now, I'm only going to draw the first one. It says sketch them all. I'm only going to sketch the first one. I mean, I want you to see how you can answer questions without having to draw all of them. But the drawing can be healthy as well. So let's take a look at A. Okay. Remember, biggest focus, what's being made at the electrodes? And A says molten sodium chloride. Ooh, molten, what the heck does that mean? Do you know? Something that is molten means it has been put into its liquid form without the addition of another substance. Usually if I was like, hey, how would you break sodium chloride apart? You'd say add it to water. And you're absolutely right. If you add sodium chloride to water, it dissociates. However, you've now created aqueous sodium chloride, which in aqueous solution is dissolved in water. Molten means that it's just NaCl. We've added so much energy to it in the form of heat, most likely, that we've broken the lattice into Na plus and Cl minus without the addition of water, all right? So it's an addition of heat, all right? Molten probably already makes you think of that because usually your brain goes to like a volcano when you hear the word molten. But it's the liquid form of sodium chloride. So let's go again. And let's create a vat that has molten sodium chloride, which means we're dealing with Na plus and Cl minus ions. we need electrodes in my vat. I like them to be made of platinum. Since it's electrolytic, it is not thermodynamically favored, so let's add a power source. There's a pretty battery. Go ahead and do a connection here. The terminal charges of the battery will directly relate to the charges of the electrodes. EPA van, am I right? So I know that my positive for electrolysis is going to be an anode. My negative is going to be a cathode. However, the anode is always the site of oxidation. The cathode is always the site of reduction. And now we just need those half reactions, right? It's the same thing we did for water. And this is easier than you might think. You can go and look at the reduction potentials, but I've given you a little trick at the bottom of this slide. If you're just dealing with these two items and one of them is metal, the metal is what wants to be reduced, all right? The metal wants to be reduced. So writing it from that standpoint will make it pretty simple. That means over here on the reduced side, the metal, which of course is the sodium, wants to be reduced, which requires electrons as reactants, which will give me sodium. So the non-metal wants to be oxidized, of course, which by definition means the electron needs to be a product. So then just complete the sentence. There is a sneaky balancing act there, which I hope you're starting to notice, but chlorine without a charge is diatomic, which means we need to balance the reaction and then balance the charge. So that's very common that that happens in this position, so I hope it's you're starting to see it quite a bit. But I have now completely answered what I need to answer. I know what is made at each electrode. Let's check it out. At the anode, chlorine gas. Right there. Well, this electrode is the anode, and the only product that's going to be left after the electrons cancel is Cl2, which will be in gaseous form, so they're bubbles. And the cathode is the cool thing. The cathode's awesome when it forms, because that sodium is going to be solid. All right, and the reason that's so awesome is because solid sodium doesn't exist in nature. It's very boom boom, so that doesn't happen. All right, so this is one of the primary processes by which we create solid sodium for use chemically. And it just gets plated straight onto that platinum. All right, and then you lift up the electrode, you can extract it off of the cathode, and you have solid sodium to play with. All right, so it's a cool process. And I meant to show you this with the water. I got ahead of myself. We're in rewind mode for a second, but I meant to show you this during the electrolysis of water part. If you look close, look, I have the setup. See the battery? I attached two wires to it. I wrapped it around the ports. See all those bubbles in there? All right, well, when I poured this water, it was just clear water. There was no bubbles. But because that battery was sitting in there, I'll let y'all come up and look at it. All of those bubbles are hydrogen and oxygen. And then if you look at the electrodes up close, it's kind of hard to see up through this, but there's bubbles on the electrodes. And if you follow those electrodes back up to whether they're connected to the plus or minus of the battery, which of course is labeled, you can figure out which bubble is which, right? If you look back at your electrolysis of water image, all right, one of them gave off oxygen, the other gave off hydrogen, and that's what's in here. So, I mean, the ones that are stuck to the glass, they've traveled off the electrode and they're all mixed up. But the ones that are on the wires, one wire is producing pure O2, one wire is producing pure H2, because I can use this. I mean, this is what we drew, the exact electrolysis of water. This will be up here the rest of the class if y'all want to come check it out at any time. You're welcome to. I did both of these, and this one has some bubbles, but this battery does not. I didn't test the battery, so. He's dying, yeah. Before we do our final examples, and I promise they'll go faster, there's a bit of notage that did not make it onto your slides. So take 90 seconds and copy that, please.
Mr. Cummings, this quality learning is currently unavailable.
Yeah, that would happen in a really, really long time. It'll come back up.
Okay.
Y'all remember at the beginning of the year when that happened, like, a lot? Remote learning, they were not prepared for it. In our next two examples, you'll notice the word aqueous. The word aqueous insinuates the presence of water. It turns out that if you dump stuff in water and it dissociates, and then you electrolyze the entire solution, sometimes just the items that you dissolved will electrolyze, and sometimes the water will instead electrolyze. And these are the rules that govern when what happens. Let me show you. I'm about to mess up this picture because look at the next example. It's NaCl again, right? But it's aqueous. So I don't want you, I know I have the advantage of a whiteboard, but I don't want you to mess up your picture. So just make notes to the side or whatever as I explain this, but then we'll do C from scratch. This is very simple. But letter B says, what if it was aqueous instead of molten? What does that mean? Well, it means right away that inside the vat, there was also water initially. What we need to know is, does water's presence affect either of the half reactions? Let's find out. During oxidation, water will take over if it's a polyatomic ion it's competing with. Is that a polyatomic ion? No. So water's presence will not affect the anode in this case. For reduction, water will take over if the thing it's competing with is a group 1 or group 2 metal. Is sodium a group 1 or group 2 metal? Yes. It's a group 1 metal. Because of that, this half reaction, when aqueous, will not happen. Instead, water will be reduced. Lucky for you, you know exactly what that looks like because we did it 15 minutes ago. What does water look like when it's reduced? I know that it's water producing hydrogen. If aqueous, this is way more boring because remember that exciting sodium solid? Nope. Instead, we make stupid old hydrogen gas and hydroxide ions in solution if water is present. Let's do the last one, but we're not going to draw a picture. I want you to see that you can think through this without all the imagery. All right, the very last one says aqueous iron 3 sulfate. All right. If we're going to electrolyze aqueous iron 3 sulfate, there are 3 things floating around in that vat. What are the 3 things? Water, iron 3, and sulfate. Those are the 3 things that would be in the vat. I need to figure out what's going to be reduced and what's going to be oxidized. I told you a good trick here is that the metal is what wants to be reduced. All right, so will water block that metal during reduction? During reduction, water will block group 1 and group 2. Iron is not one of those. Therefore, he will reduce as normal. Reduction means that electrons are reactants. So there's your reduction equation. That means that the sulfate wants to be oxidized. Will water compete with sulfate? During oxidation, water takes over polyatomics. Is sulfate a polyatomic? Yup. That means that this dude does not get to play our little game. Instead, water will oxidize, which of course we know produces oxygen. Hey, in electrolysis reduction, that top one takes place at the cathode. So we've got a red cat. So what's going to be produced at the cathode? Iron. Oxidation takes place at the anode. So what's going to be produced at the anode? Oxygen and hydrogen ions. I mean, oxygen gas and hydrogen ions. And without drawing the picture, I was able to draw the same conclusion.